Okay, now I want to talk to you about integration by substitution. Let's say that you want to evaluate this integral. Now, you can see here that you have a function raised to a power here. And you might remember that we had a simple power rule for integration to actually integrate the variable raised to a power. But here we have a function raised to a power. So that's not as simple. So what we want to do is we want to see if there's a way that we can change variables and get the integral into this form u cubed du. Okay, so let's take a look at what we might be able to do. So since this is a power, what I'm going to do is I'm going to let the expression that's raised to this power be u. Now watch what happens when I do that. If you let u equal x squared minus 4, then the derivative of u with respect to x is 2x. Now you can just multiply both sides by dx and get du equal 2x dx. Now on future examples I'll just do this step, because really you're going to see that du, if you let u be a function, then du is just the derivative of that function. In this case it's just the derivative of x squared minus 4, which is 2x times dx. So du is just the derivative of u times dx, and that's all you have to do. So you don't need this middle step. Okay, so if we let u be this, now I like to rearrange my integrals when I'm doing this u substitution so you can actually see the u to the power and the du. So right here, in here you can see that that is actually u cubed, right? Remember u is x squared minus 4, so that's actually u cubed. And then if you slide that over here, you can see that this part is just du. So basically what I've got is I'm able to write this integral as u cubed du from a to b. Now here's the catch. I don't know what a and b are because I changed variables. When you change variables, that's going to change your limits. So if I change variables, I got to change these limits. So these limits, instead of being from 1 to 3, I need to find the new limits. So what I need to do, I need to find the u limits. I need to change from the x limits to the u limits. Well, that's easy enough. Here's the u in terms of x. So if you plug x equal 1 in here, you get negative 3. So you get negative 3. So when x was 1, u is going to be negative 3. And then if you plug 3 in, 3 squared minus 4 is 5. So when x was 3, that changes to u equal 5. So now this integral can now be written as u cubed du from negative 3 to 5. And we can integrate this using the power rule, u to the 4th over 4 from negative 3 to 5. And then you just plug 5 in for u, which is 5 to the 4th over 4, and then minus negative 3 in for u, so negative 3 to the 4th over 4, and then you get 544 over 4, which is 136. Well, that leads us to this general power rule for integration. So the general power rule for integration looks like this. If you want to integrate u to the n du, that's u to the n plus 1 divided by n plus 1 plus a constant. Well, you may think, well, we've already covered this rule, but we really haven't covered this rule. What we covered was the simple power rule for integration, for when you have x to a power. This is for when you have a function of x to a power. Okay, now I'm going to show you in a minute how we can manipulate these functions so that we can get it into the integral into this form. But make sure you understand, the only reason I can work the ones that I'm going to show you is because I've set it up in such a way that I can get it in the proper form. If I had just given you this function here in that previous example without the 2x in it, if I'd just given you this, then if I didn't have the 2x in it, this wouldn't be du. So I actually wouldn't be able to use this method if I didn't have the 2x in it. So this only works in certain circumstances. But if you do enough of them, you'll get to where you can recognize where this would be used. Okay, so notice here I have an integral 3x squared times x cubed plus 2 raised to the fourth. Well, since x cubed plus 2 is raised to the fourth power, I'm thinking maybe I can write this as u to the fourth. So this integral might be able to be u to the fourth du. Well, if you let u equal the binomial that's in the parentheses, and then you calculate du by saying the derivative of this times dx. So the derivative of this would be 3x squared times dx would be dx. Now, I'm going to take the 3x squared and the dx, and I'm going to put them together so you can see that. Okay, now, so what you've got here, remember this is u, so I have u to the fourth, and this worked out to be exactly du. So I have u to the fourth du. So I can write it like this. Okay, now again I have to come up with a new set of limits. So what I do is, here x was 0, so plug 0 in up here and get u. So when x is 0, u would be 0 cubed plus 2, which is 2. And then here when x is 1, u would be 1 cubed plus 2, which is 3. So for u, the limits of integration will be from 2 to 3. And now we can integrate u to the fourth du using this power rule up here, and we get u to the fifth over 5. And then you can evaluate that from 2 to 3. And so you get 3 to the fifth minus 2 to the fifth. And then you can, use a calculator or whatever you need to finish that evaluation using the fundamental theorem of calculus. Okay, now you might have noticed here I didn't switch this integral back to the x cubed plus 2 because you don't have to. As long as you change the limits of integration, you can apply the fundamental theorem of calculus to this just as if it was x. But again, you've got to make sure you change the limits of integration to do that. Now, if you wanted to, you could change this back to x cubed plus 2, but if you do that, then you need to leave the limits, change the limits back to 0 and 1. So I find it easier just to leave it in the u form. Okay, now here's another one. Notice that I have cosine of x raised to a power here. So I have cosine x quantity squared. And you might realize that I have minus sine x. And if you think about cosine x, the derivative of cosine x is actually minus sine. So if I were to let u equal cosine x, then du would actually be minus sine x dx. So really this minus sine x and this dx, if you put them together, that forms du. And since cosine x is u, then I have the integral u squared du. So I can write it as integral u squared du. And then of course I have to get my new limits of integration. So if x is 0, let's see what cosine of 0 is. Cosine of 0 would be 1. And then if x is pi, what's cosine of pi? Well, that's going to be negative 1. So you can see there I'm integrating from 1 to negative 1 u squared du. And then if you integrate u squared du, you get u cubed over 3. And then you can evaluate it at negative 1 and then subtract the same thing when you evaluate it at 1. And so that's going to be minus 1/3, which is minus 2/3. So basically, now on these, both of these worked out perfectly. On these, I actually had the 3 here, and here I had the negative 1 for the sine x. Now, what if I had not had the 3, or if this had been just sine x and not negative sine x? Well, there is a way you can manipulate integrals, and what you do is you multiply the inside by whatever constant you need, and then you multiply the outside by the reciprocal, okay? Because then you're just multiplying by 1. And let me show you an example. This is basically very similar to the example I just did. But notice I don't have 3x squared, I just have x squared. Now I'm going to do it the same way. So u is going to be x cubed plus 2, but du is still 3x squared dx. So what I need is I need a 3 in here. Well, you can multiply the inside of an integral by 3 as long as you multiply on the outside by 1/3. So that's what I did down here. Notice that I multiplied the inside by 3 to get 3x squared dx and the outside by 1/3. Well, now this is in the form u to the 4th, and then this is du. So I have u to the 4th du. The only difference is I have to have that 1/3 with this integral. And you just integrate this just like before, except instead of u to the 5 over 5, you have u to the 5 over 5 times 1/3. So that's actually going to be u to the 5th over 15. So you evaluate u to the 5th over 15 at 3, and you get 3 to the 5th over 15, and then evaluate it at 2, and you get 2 to the 5th over 15, which gives you 211 over 15. Notice that when I changed my variables, they changed to the same values because I was using the same substitution. Okay, now here, notice I don't have the minus here like I had before. Well, if I let u equal cosine x, well, du is still minus sine x dx. So what I could do is I could multiply the inside of this by minus 1 and the outside of this by the reciprocal of minus 1, which is, of course, minus 1. And so if you do that, you'll get a minus 1 on the outside, and then on the inside, you'll have the minus sine x dx, which you need in order for this to be in the form of u squared du. So now it's u squared, and this is du, so you just get u squared du, but you have a minus on the outside. And notice that I still got the same change of variables of values here, 1 and -1 as I had before, because I used the same substitution. So u cubed over 3 is the integral of u squared, but I have that minus 1 out here, so I actually have minus. So when you evaluate this, you get minus 1 quantity cubed over 3 with a minus 1 in front of it. That's going to be 1/3. And then you're going to have minus, and then you're going to have minus 1 cubed over 3, which is minus 1/3, but you have a minus minus 1/3. So that's going to be 1/3 plus 1/3, which is 2/3. And let me show you some more. This one here, since I've got x squared minus 1 raised to a power, I'm going to let u equal x squared minus 1, and then du is 2x dx. Well, notice that I have x and dx, so I had x and dx in the original problem, but I didn't have a 2. So I went ahead and multiplied the inside by 2, so I would get a 2x dx, so that I would have du. But if I multiply the inside by 2, I got to multiply the outside by 1/2. It's reciprocal. So that's okay. And so now I have u cubed du. And so we can integrate u cubed du as u to the 4th over 4, but we have to multiply that by 1/2, so it's really u to the 4th over 8. And then you evaluate it at 3 and get 3 to the 4th over 8, and then subtract 0 to the 4th over 8, so you get 81 over 8 for the answer. And then this one, look at tangent. See, this is really the tangent of x to the 4th raised to the 5th power. Okay, so another way to write that is tangent of x to the 4th all raised to the 5th power. So really, if I let u be the tangent of x to the 4th, then du would be the derivative of this. Now the derivative of tangent u, remember, is secant squared u times the derivative of u. So it would be secant squared x to the 4th times 4x cubed. Well, if you notice here, I've got the x cubed and I've got the secant squared. So I've got the x cubed and I've got the secant squared. What I don't have is the 4. So if I multiply the inside by 4 and the outside by 1/4, that'll fix that. So now this is du, and so I have u to the 5th du. And of course you have to change your limits. Don't forget the 1/4 on the outside. You have to change your limits. Tangent of 0.1 to the 4th is just tangent of 0.0001, and tangent of 0 is just tangent of 0, which is 0. So if you integrate this, you get u to the 6 over 24, and then you can evaluate it from 0 to tangent of 0.0001, and then you get this as your answer. You can read this little blurb down here. If you need to pause the video, pause it. In the next video, I'm going to show you how to handle some of these examples that involve trig functions.